Hi, and welcome to another old steam-powered machine shop where there's no indexable tooling, digital calipers, or DROs. In this episode, we got the planer test piece finished and evaluated. The Lily steam engine, that's the next big overhaul in the shop, is completely apart and evaluated, and I'll show you about that. And also finished up the speed increasing countershaft for the DC generator that's going to make some DC lighting here. So appreciate the support and the likes and the comments especially, and we'll get right to it. I'm setting up the old Brown and Sharp milling machine to cut a 1/4 inch keyway in the generator shaft, countershaft. And I got a cutter here. Really early milling machines used a center similar to a lathe center on the end of the arbor instead of a running bushing, which is okay for pretty light work. This is my stop wedge. Drive in there to lock it up so I can loosen the nut. To line the cutter up in the center here, you can just take a piece of thin paper, put it in here. Bring the cutter over till it touches. Add about another 5/1000. And you take the thickness of the cutter and the diameter of the stock, add them together and divide by 2. And that's how far you set the cutter over. And I'm just going to use the dial here. Okay, that's 1.25 inches plus 1/4 inch. That makes it 1.5 inches. So that would be 3/4 inch set over, 750. 2, 4, 6, 7, 10, 20, 30, 40, 50. Got the afternoon sun in the window here to contend with. Maybe you can see. This keyway has got to be cut an 1/8 inch deep, 1/4 inch keyway. And I wanted to start a little bit before that mark and do the full keyway by the end of that mark. So I'm going to start it up, engage the feed, and then plunge the cutter down 100 thousandths to take 100 thousandths for the first pass. Pass down to 125 thousandths on the gauge. So we'll see how it comes out. A lot of chatter when it was cutting it, but pretty good result. Oh, there's the finished key set up in it. Looks like it'll work fine. I'd say those 5/8 set screws were big enough, but that's the way they were. Now over here on this end, I'm gonna, instead of putting a keyway, I'm just gonna cut a flat along here for the set screws to set down on, because that pulley hub is so long that it gets really difficult to broach a keyway in it. And it's not going to have that much force on it anyway. It's the smaller pulley, so it won't have nearly as much torque on the shaft. So, and it's got 2 set screws. So I'm just going to put a flat along here for the set screws to seat in, so that when the set screws kind of booger up the shaft, you'll still be able to move the pulley around. Here's a shot of the countershaft in place for the generator. Now I got to make up some belts for it. See how it goes. The tapered key came out easily on this side and the pulley came off. This is the governor pulley that runs a 1.5" flat belt. Excuse me. 1.5" flat belt. It's kind of strange that there's paint on it, which might shed some light on the history of this, like it was kind of a hack and slash restoration that never got put into use. Well, that's going to come right off. I think I'll heat that just a little bit. Expand it and it'll come right off. Tapered key. Oh, look at that. It's hollow. Hollow with a keyway. I haven't really taken any time to clean up any of the parts yet, but I wanted to take some time to show you a little bit about the design of this engine. It's in surprisingly good shape. The overall consensus is that it's not going to take a whole lot to get this in really good shape. The connecting rod is very similar design to the Morris. It looks like it's a forging. There's a parting line here. And you can see part of a parting line there too. But it's kind of elegant the way it was machined, and it can be done in a horizontal mill with a wide cylindrical cutter. Make a cut here, here, and here. It's kind of elegant and very simple. I like it. The brasses go together almost identical to the way the Morris was. The wedges are a little different. On this one, these wedges move slightly to take up the bearing. The brasses, this brass here is free to move when it's up close, and this wedge, there's two set screws, threaded set screws with lock nuts that go in from each side. So by tightening one and loosening the other, you can move this wedge, which has quite a steep angle on it, and that will actually goes this way. And that will push the brasses together. Works the same way on the other end. The brasses themselves seem to be in pretty nice shape. although we'll probably resize them by machining some off the parting edges and then clamping them together and then boring it back out to the pin size, less a couple thousandths for lubrication clearance. The dimensions are 6 by 6, same as the Morris, and everything looks pretty good. Nothing really gave me a problem. There was some water at one time in the steam chest, and the slide valve is a little crusty, but at least there is a slide valve. The other parts came apart pretty well. Eccentric. Rod is very similar to the Morris. The setup on it with the brasses. Piston looks pretty good, and the bore looks pretty good. The Babbitt, I don't know if it's original or not, but it seems to be in pretty good shape. Same deal there. It can be, there was a lot of shims in it. I mean, very thick shim, so I got a lot of room. It could be shimmed down and then line bored straight again. The crosshead slides are not pitted or screwed up. The eccentric is grooved up pretty good, which is what you'd expect with cast iron against cast iron. I don't know why they made them that way. It's kind of a cheap way to do it, but this flange in the center keeps everything lined up. So I don't know, I may have to make an offset fixture for this and just machine enough off of these surfaces to clean it up, and then cut the edges here, put the eccentric back together again, and then bore that out to match with a couple of shims in here for to take it up for wear. The piston is one piece with two rings with a staggered joint. Appears to be in pretty fair shape. It'll be very interesting to see what the clearance is on this as is. The connecting, or not the connecting rod, but the piston rod here is pretty pitted, and that'll be replaced with a stainless steel, polished stainless steel piece. Which leads us to the first major thing that I don't like about the design of this engine. The packing gland is a three-piece affair that goes through the back head, through the frame, and then this nut goes on and tightens it down. It turns. There's no way to lock it. There's no way to tighten the nut. You can't hardly get on the nut anyway. You have to do it with a punch or something. And it's just asking for trouble. And I'm not sure how I can change it, but we'll get into that later. The slide valve is a nice design. It's machined on the edges, and it's a little pitted up, but we'll fix that up. The cylinder has had rain water in it, and it's a little crusty. I may end up remachining that. I think I can reach down in there with a end mill and machine that to resurface it. That's one of the reasons why most of the model designs, and if I ever get into building a cylinder, I'm going to have the steam chest here unbolt so that these port surfaces are clear, easy to machine, and it makes the casting simpler. You can imagine this is a pretty complicated casting, and it's got the steam ports cored into it. This is the jacket that goes around the outside of the cylinder here. It looks to be copper. I can't believe that's the way it was originally. I think originally it was brass, but this will straighten out okay, I guess. What it did is it left an airspace in here that was to insulate the cylinder, to keep the cylinder itself, this area in here, hot so that the steam wouldn't condense. Sometimes they inlaid wood in here, tongue and grooved hardwood. You could actually put a sheet metal shroud on it and fill it with some type of modern insulative material that would harden up. Greatly increases the efficiency of the engine if you can keep the cylinder hot. But that's about as much as I've looked at so far. This is the slider for the valve, and it's pretty heavily pitted, but I think, you know, 10 or 15 thousandths off of each side, it'll clean that up, and might even remachine that. The rod is threaded in here. This will get replaced with stainless. These are the bearing pieces that go against the rod crosshead, and it's typical design. They're corner to corner so that when you tighten them up, it takes up both directions at the same time. Kind of a neat design, but a little complicated to make. I don't know if it's really necessary, but these will clean up and shim them down to tighten them up. And as you saw, the governor gear is a strange bird. It's hollow. Why they did that, to save cast iron or weight, I do not know. But it was on there pretty tight. Now the crankshaft is kind of an unknown at this point. I cannot get the flywheel off, or I haven't been able to yet, I should say. It moved a little bit and stopped. I'm wondering how important it really is to get it off of there. I mean, I would hate to destroy it getting it off just to make it easy to clean up and machine. The crank itself is kind of a typical design. I've seen it in a lot of other stationary and traction engines. The crank is actually made in one piece, probably machined out of a billet, large billet with the offset in it, and then these cast iron counterweights go on each way and fit around the outside of the crank, and then there's a pinch bolt tightening them down. So this isn't actually part of the crank. This is the cast iron covers over the end of the crank that carry the counterweights. The bearing surfaces are surface pitted a little bit. I think they'll polish up okay. Without having to grind anything. And the pin looks really nice. It had a lot of grease in there, preserving it. The flywheel, I like to shut off the compressor and be right back. And the engine frame bare. A lot of things about this engine I don't like the design of. For one thing, you can't get to the bolts or to the nuts to get the cylinder off, and there's a lot of other little details that could have been engineered a little bit better. I think I will forego the I-beams and make some timbers for skids for it to bolt to. One thing that's kind of amazing to me is that there's absolutely no public record of Lilly Machine Works in Erie, Pennsylvania. After 1900, Erie was a tremendously industrial place. There was all kinds of manufacturing going on there. A lot of engines were built there, gas engines, natural gas engines for the oil business, steam engines, Skinner Engine Company, and the Shea locomotives were built there, all kinds of machinery. But Lilly Machine Works kind of got lost, and I don't know how many engines they built or what sizes. I can find no record of another one anywhere. If you're a viewer and you've ever heard of a Lilly engine, I'd appreciate knowing about it. Well, the story with the new coal is a little disappointing. It makes a nice steady fire, but it just doesn't make enough heat, and I don't really know why. I'm pretty sure the grates are not right for this, and I also don't have enough draft for it, and that would require a taller chimney, which is a big deal. So I've tried running a thick fire, I've tried running kind of a thinner fire, I've tried it with all the draft, I've tried it with a little bit of draft, and it just, like, I've got the heating system on today, and that's some load on the boiler, but really have a hard time getting above 50. So I want to run the engine, do some work. So I'm going to put some wood in it, get the steam up. This is an interesting book put out by the Hine Boiler Company. (1896). And a very interesting thing about steam is it's probably the most amazing medium for transferring power and converting heat energy into something that you can use. And steam follows some very solid guidelines and rules, and one of them is found in the steam tables. And you can, if you study thermodynamics at all, you'll spend a lot of time with steam and a thing called steam tables, which are the properties of saturated steam, and that's steam that's produced under in captivity, and it builds up its own pressure in relation to the temperature that it is. So for any given temperature, the pressure will be a certain amount, and vice versa. For every pressure, the steam will be a certain temperature. And in this column, it's laid out in every 10 degrees. The engineering books lay out the steam tables like in every degree. But say it's 65 psi, saturated steam would have a temperature of 311.54 degrees Fahrenheit. So if you look at the boiler here, right now we got 65 psi. And according to the book, that should be 311 degrees. And you can see it's about 21 degrees short because the outside of the boiler is not as hot as the water and the steam. But if you can check it, and it's within a degree all the way around and up and down. 289, 291, 289, 289, 283 over here close to this handhole. This is the square nose finish tool, and I'm taking a light cut just to see what kind of surface finish I can get from it. Well, it does just what you'd think a real wide, flat tool would do. Chatter. But wait, it might not be chatter. These lines are all exactly lined up with each other. Chatter would be a random kind of a thing. But these marks are all in line, which makes me think it's gear teeth marks from the worn gears. It's setting up a vibration on every pass exactly the same. So, to get a really good finish out of this machine, we're either going to have to do something about the gearing, or else find a tool that minimizes that. The last pass was with a shear cut tool. It's sort of like the flat nose finish, except it's got a very steep angle. It didn't make much difference. It still did about the same thing. I'm going to go back to a tool ground more like a lathe tool with a very small radius on the point, and slow the feed down. You're supposed to run a real big step over feed with these tools, and it'll take longer to get across, but I'm going to slow it down to about maybe 20 thousandths per cut. Take a light cut across it and see what that looks like. That's it for the test piece. The surface finish is better. It's really very smooth, and you can just barely feel those grooves in there. But it could be better. This is a engine machinist straight edge made. It's got a ground surface on the bottom, and it's used to check the straightness of cylinder heads and the tops of engine blocks. It's definitely not the quality that you would use for scraping, but it's pretty good, and I've taken care of it. So I've got it set up on my test piece here that I just took out of the planer. I put some layout dye on it, but it won't work the way it would if you were scraping something. So this is a 1,000th feeler strip, and I don't know if you can see on it, it says Starrett 1,000th. A little loose right there, but there's still drag on it. Same thing there. Tighter up there. Tight there. So there's a little bit of a depression in the middle of it, less than 1,000th of an inch. Not bad for a 135-year-old machine. More accuracy than I expected out of it.